In this next section, we're going to take a look at multiplying and dividing radicals. So before we get to the problems, a little bit of information you're going to need to know. For radical operations, in order to multiply or divide radicals, the index must be the same on both radicals. Then what you're going to do, once you've determined that the indexes are the same, then you're going to multiply or divide anything that's alike. So if you've got what amounts to a coefficient on the outside, you're going to multiply the coefficients together. Then whatever your radicands are, you're going to multiply those radicands together. And then you may need to simplify once you're done with that. So starting with problem number 1a, we're asked, can you simplify the product of the radical expressions? And then explain. So we're given the cube root of 6 times the square root of 2. And you cannot multiply these together because if you look at the indices, the first one is a 3, the second one is a 2, so that means that they cannot be multiplied together. In problem number 1b, we're given the cubed root of -4 times the cubed root of 2. So again, we're going to take a look at the indices. Are the indices the same? We have a 3 and we have a 3, which means we can multiply them together. Now, for both of these, the coefficients are 1, so we're not going to bother with anything there. We're going to look at the radicands. We have a -4 and a 2, so multiply -4 times 2 and you get -8. So now we're left with the cubed root of -8, which is -2. For problem number 2, we're going to look at what is the simplest form of the cubed root of 54x to the 5th. So what we're going to do is we're going to do a couple of different things depending on if we're looking at an integer or if we're looking at a power. So that first number that's underneath in the radicand, the 54, what we want to do is we want to try to break this down into a perfect cube if we can. So we're going to factor the 54 and look for a perfect cube. So what are the perfect cubes? You've got 2 cubed is 8, 3 cubed is 27. So 27 does go into 54 2 times. So we can take that 54 and change it into 27 times 2. Then we'll take the index, which is 3, and we're going to put that underneath the exponent of the power, which is 5. And what we're really doing here is we're going to be dividing that 5 by 3. The quotient is going to come outside of the radical, and the remainder is going to stay inside of the radical. So we can see that we've got the cubed root of 27 times 2, x to the 5/3. That x to the 5/3 isn't really there, but I'm just putting it there to show you what exactly the line of thinking is. So the cubed root of 27 is 3. That's going to come to the outside of the radical. Then 3 goes into 5 one time. So since 3 goes into 5 one time, we're going to take 1x out of the radical and put it next to the 3. Then we've got a 2 that's left over. And then when we divided the 5 by 3, our remainder was also 2. So that means that we've got an x squared that's going to remain on the inside of the radicand. So that means our solution is 3x cubed root of 2x squared. Next up, we've got what is the simplest form of the square root of 72x cubed y squared times the square root of 10xy cubed. With this, there's going to be multiple ways that we can do this. So I'm going to show you 2 of the ways that this can be done. The first way, we can just go ahead and multiply everything through. So we're going to say the square root of 72 times the square root of 10 is the square root of 720. X cubed times x is x to the 4th. And y squared times y cubed is y to the 5th. Then what we would do after that is we would see if we could break 720 down into a perfect square. So the biggest perfect square factor that we've got for 720 is 144. 144 times 5 is 720. So then you can take the square root of 144, that's going to give you 12. Then how many times does the index 2 go into x to the 4th? It goes twice, so we're going to pull an x squared out of the radicand. There's not going to be anything left in because there was no remainder. then how many times does the index go into y to the fifth? 2 into y to the fifth. It goes twice with 1 left over. So we're going to pull a y squared outside of the radical and leave a y to the first inside. So that means you're going to have 12x squared y squared square root of 5y as your solution. Now we're going to take a look at another way of doing this, one that keeps the number smaller and maybe a little bit more manageable. There are going to be more steps, but you can probably do this in your head rather than having to try and take out a calculator and figure this out. So instead of just multiplying 72 times 10, what we're going to do is we're going to look to break down the 72 and the 10 if we can. Now 72, we're looking for a perfect square factor. The biggest perfect square factor for 72 is 36. 36 times 2 is 72. So then we know that the square root of 36 is 6. So we can actually pull that out of the first radical, and then we'll look to simplify the x cubed and the y squared as well. So go back to your index. You've got a 2. How many times does 2 go into x cubed? It goes once with 1 left over. So we pull an x out, leave 1 x in. 2 goes into y squared once, so pull a y out. You don't have anything left over with the y. Now on the second radical, you've got the square root of 10xy cubed. Now 10 cannot be broken down into a perfect square factor. So we're going to leave the 10 as is. We can't put 2 into 1 for the x to the first, so we're going to leave the x where it is. But we can take 2 and put it into y cubed. So 2 goes into 3 one time with 1 left over. So we're going to pull 1y out, leave 1y in. So now we've got 6xy square root of 2x times y square root of 10xy. Now what we'll do is we'll multiply the coefficients and then we'll multiply the radicands. So your coefficients are 6xy and y. So 6xy times y is 6y squared. Then your radicands, 2x times 10xy, 2 times 10 is 20, x times x is x squared, and then you have a y. Now we need to look to simplify if we can. So look at the 20 first. Are there any perfect square factors of 20? Yes, there's 4, which is a perfect square factor. You multiply that against 5 and you get 20. Then we're going to be looking at, can we do anything with the index and the exponents on the variables? So when we look at, again, the index is 2, we have an x squared. 2 goes into 2 one time, so we're going to pull 1 more x out. We're going to leave the y in because we can't put 2 into 1, and then we're going to simplify this down. The square root of 4 is 2, so pull the 2 out, multiply that against the 6, and that leaves you with 12. We pulled 1 more x out, so now we've got an x squared along with our y squared, and then on the inside of the radical we're left with 5y. So the solution is 12x squared y squared square root of 5y. Now a little bit more information that you're going to need when dividing radicals. We can look at division of radicals in one of two ways. We can either look at it as a division problem located underneath a radical, where we have the square root of x over y, or you can change that into two separate radicals in one fraction problem. So the square root of x over the square root of y. You can do it either way, and you can change it from the single radical to the two radicals, or you can change it from the two radicals to the one radical, depending on what's going to be best for you in solving a problem. In 4a, we're given what is the simplest form of the expression, the square root of 18x to the fifth over 2x cubed. So what we can do with this is we can take anything that's in the radicands and we can go ahead and divide them. So again, there's going to be more than one way of doing this. So I'm going to show you two separate ways. The first way, I'm going to go ahead and break down that 18 into a perfect square factor and another factor. So we get 9 times 2, 9 being the perfect square, and so it's 9 times 2, x to the fifth underneath that radical. We'll leave 2x cubed the way it is on the bottom. Now, at the top, We'll go back and we will take the square root of 9, which gives us 3. And then, again, the index on this is a 2, so how many times does 2 go into 5? It goes in twice, so we're going to pull out an x squared. Then what do you have left as a remainder? You have 1x left as a remainder, so we're going to have just an x left inside. So 3x squared, square root of 2x. Now going down to the denominator, we're going to do the same thing. We can't do anything with the 2, but we can do something with the x cubed. So what's the index? You've got an index of 2. 2 goes into 3 one time with 1 left over. So you're going to pull 1x out, keep 1x left in. So x square root of 2x. Now what we can see is that we've got some reducing that we can do. So x squared divided by x leaves you 1x in the numerator. And then the square root of 2x, the 2 square root of 2x's cancel out. And so you're left with just 3x. Now the other way that we can do this is we can start by dividing first. So 18 divided by 2 is 9. X to the 5th divided by x cubed is x squared. Remember that when you're dividing exponents, then you subtract the exponents. So it's x to the 5th minus 3. Or another way you can think of it is you've got 5 x's lined up across the numerator, and you've got 3 x's lined up across the denominator. You can cancel out 3, so that means you're left with 2 in the numerator. So that means that you've got square root of 9x squared. Now, what's the square root of 9? It's 3. What's the square root of x squared? It's x, so your solution is 3x. For 4b, again, I'm going to show you a couple of different ways to solve the same problem. So this time you're given the cubed root of 162y to the 5th over the cubed root of 3y squared. So taking the first method, we're going to simplify the radicand. So 27 times 6 is 162. So 27 being a perfect cube. And then we know that we'll be able to do something with y to the 5th. There's nothing we can do in the denominator with 3y squared. So we take the cube root of 27 and we get a 3 that comes outside of the radical. Then with y to the 5th, we're going to divide the 5 by 3. 3 goes in one time, so we're going to pull 1y out. The remainder is 2. So that leaves a y squared in the radicand. So now we've got 3y cubed root of 6y squared over the cubed root of 3y squared. Now we can start dividing the radicands. So 6 divided by 3 is 2. Y squared divided by y squared, that's just 1, it cancels out. And so we're now left with 3y cubed root of 2. If we do it the other way, which is to divide the radicands first, 162 divided by 3 is going to be 54. Y to the 5th divided by y squared is y cubed. So now what is a perfect square factor of 54? 27 times 2. So you get the cubed root of 27 times 2y cubed. The cubed root of 27 is 3. The cubed root of y cubed is just y. So then you're left with the cubed root of 2 inside the radicand, or the cubed root of 2 next to 3y. So your solution is 3y cubed root of 2. Again, you see that it doesn't matter which method you use, you're going to arrive at the same answer. All right, another piece of information that you need to know is that denominators cannot have radicals in them. So what this means is that we have to rationalize any denominators that have a root or a radical in them. So in order to rationalize a denominator or remove the radicals, the value of the exponent in the radicand must become a multiple of the index. So let's say that you have a square root. That means that all of the exponents in the radicand have to be even numbers. 2, 4, 6, 8, 10. Can be any of those, but they have to be an even number because even numbers are multiples of 2. If you had a cubed root, then your exponents in the radicand would have to be either a 3, a 6, a 9, a 12, anything that's a multiple of 3. If we're looking at 4, as our index, then the exponents would have to be 4, 8, 12, 16. Now they don't all have to be the same exponent. Each one just has to be a multiple of the index. So then what you're going to do is multiply the numerator and the denominator by the rationalizing radical. So the example that I've given you here is that you've got y over the cubed root of x to the fourth. So we've got a cubed root in the denominator, which means we need to get rid of it. We look at the exponent and we've got an x to the fourth. Well, since we've got a cubed root, we need that 4 to become a 6. That's because that's the closest multiple. Now you could do this by going to the next multiple of 9 or multiple out past that of 12, but you're just going to end up doing more work for yourself. So we want to make that x to the fourth and x to the sixth. Well, what do you have to multiply x to the fourth by to get to x to the sixth? You would have to multiply it by x squared. So what we're going to do is we're going to multiply the denominator by the cubed root of x squared. Whatever you do to the denominator, you also have to do to the numerator. So when we do that, we would end up with y cubed root of x squared over the cubed root of x to the sixth. Now once we're there, we're going to simplify. There's nothing that can be done with the numerator, so you're going to work on the denominator. How many times does 3 go into 6? Twice, so that means you're left with an x squared. So y cubed root of x squared over x squared. There's nothing that can be simplified once you're there. In problem number 5, we're going to take a look at one of these examples and we're going to rationalize the denominator. So we're given the cubed root of 5x squared over 12y squared z. So let's take a look at what we've got to do first. We're going to simplify the radicand if possible. And we've got a 5x squared in the numerator and a 12y squared z in the denominator, so there's nothing that can be done in order to simplify those. So the next thing that we're going to take a look at is we're going to rationalize the denominator. So the denominator is a cube root. So that tells us we're looking for exponents of 3, 6, 9, 12, 15, da 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 da. We have a 12 to the first, a y squared, and a z. So what we want to do is we want to get to 12 cubed, y cubed, and z cubed. So what do you multiply 12 by to get to 12 cubed? You would have to multiply it by 12 squared. What do you multiply y squared by in order to get to y cubed? You would multiply by a y. And then what do you multiply z to the first by to get to z cubed? You would have to multiply by z squared. So we're going to multiply both the numerator and the denominator by the cubed root of 12 squared yz squared. When we do this, what we should end up with in the denominator, if we've done it correctly, is just a 12 to the first, a y to the first, and a z to the first. So that's what we do get. We get 12yz in the denominator. Up in the numerator, though, we had to do 12 squared, which is 144, times 5, which gives us 720, then x squared y z squared. Now we've got to try and simplify the radicands if possible. So here's what we're going to do. We're going to look at that 720 and we're going to say, is there a perfect square factor, or I'm sorry, a perfect cube factor that goes into 720? And we do. We have 8 times 90. So we get 8 times 90, x squared y z squared. Now notice that there's nothing that we can do with that x squared y and z squared because they're all the exponents are smaller than the index. So we're going to take the cubed root of 8, that gives us 2, and then we're left with 90 x squared y z squared in the radicand over 12yz. Now what we can do is we can take that 2 and that 12 and we can cancel those out, or we can reduce those. The 2 goes away, the 12 becomes a 6, and your answer is going to be the cubed root of 90x squared yz squared over 6yz.